Hello. Today I'll talk about the transformer attention algorithm and show why it is working and what are the mechanics the, of this attention algorithm. So this episode was inspired and in large part follows by this Medium article by Daniel Warfield and the Medium article. But the number has been changed to make it more realistic. All right. So the transformer attention algorithm. So what it's trying to solve basically um, is like if there's a sentence like this apple is red, then I guess red and apple, it's like kind of related, isn't it? Red basically describes Apple, and this or is are kind of less relevant. So which word should? So when Apple is here already, it's trying to Transformer is trying to predict the next word. So people say what it means is that when the Apple word shows up, which word do you expect? And eventually, a very high likelihood is red, isn't it? So this is sort of an algorithm that does that stuff. Um, so it basically produces a compatibility score for every pair of words and uses those scores to decide how much information to pass between them. Um, so we'll walk through the exact arithmetics of this attention on this particular sentence, this apple is red, and show the resulting attention heat map so that how the correlation actually works out. And it basically has like four steps. Define the input and define the learnable parameters, which um, in reality, this is where a transformer has to be trained on large number of articles, like the whole world of internet, Wikipedia, everything, to get those matrices right. Um, Here I'm just making up some. So yeah, and then calculate the query key and value. Um, so what this query is like in a sentence, it basically is this is an apple. Like, so what is Apple looking for? I am looking for a verb. I am looking for an adjective, adverb, a noun. So what is it looking for? So this is the query. The key is for each word, they will announce who they are. Like it's like a posting a CV, like apple, oh, I'm a noun, okay? Red, oh, I'm an adjective. So this is what the key says, that who am I? Query is whom I am looking for, okay? And then there's the resulting value that gets in, okay? So it divides into multiple heads so that it actually tries to do various contexts. So one would be a grammar, like what kind of verb or noun or something there should be. The other one is that what kind of context there should be. And there are many kind of different um, nuances that a sentence needs for the next word. And each different heads will do those kind of things. So divide multiple heads, calculate the Z matrix. It's a kind of a compatible score. Um, Masking is something that for GPT kind of algorithm, we don't want the future word to in the later part of the word to appear in the later part of the sentence to relate to the earlier appeared words. We want only in one direction, so we basically mask the future words. Calculate the attention matrix, so scale it to sum up to one, and then calculate the attention head output, um, and then concatenate all these heads. So this is sort of what we'll do. So let's first set up the Google and then define the input. So this is the word of each sentence in a numerical vector. So it's called embedding, right? And it processes like this multi-head self-attention, basically processes sequence of vectors, and it's like a token. And well, we need those words to be in token, right? So, so notice that the two function words, this and is, have very similar embeddings in very first dimension. Okay, and this and is. Uh, And the two content words apple and red also share some similarity, all right? Um, so this is how embeddings basically, the standard ways of doing it basically represent the words, okay? So here's our input matrix that put those in, okay? And then define learnable parameters. And again, these are kind of um, has to be trained by the transformer in reality, but I just made up some numbers that would give some intuition. So query is what kind of person am I looking for example. Key is what kind of person am I? And then the value is what useful information do I carry? Something like that, right? So, so we are trying to basically play with these three entities. So each weight matrix in this example is a real transformer. In a real transformer, these are start as random guess and then will be updated with many, many sentences, like the whole web of the world. Um, okay, so here we are. So now we have query key and value. So we basically query is an input times the Q matrix, key is an input times the K matrix, value is the input times the WV matrix. So we compute them. Okay. And then dividing into heads for different contexts, basically split these pieces, the head, so they can specialize in detecting different type of word relationship. Um, so head one gets the 0 and 1 column, and head two gets 2 and 3 columns. So we basically cut them here, these two and these two. So for each of these three sets of these matrices. Okay. So, so head one, head two, things like that. Okay, and then calculate the Z matrix. This computer score for every pair of words that measures how much should word I pay attention to the word J. Okay, so word I to word J, kind of the relationship. That's the Z matrix. So query and keys. Whom am I looking for and who I am each word. So if they have a high match, that is who I'm looking for and who I am, kind of are really highly related. So this is basically what this step is doing. And you can see here. Of course, itself usually tends to be usually a high number. And then there's a masking. So what this masking does is that the causal mask is that we basically put minus infinity in a softmax relationship such that the future words, the word that has not appeared yet from when there's a word, um, um, will be just discarded in the softmax. So this, so apple. So for example, apple, row one can see this, which appeared before apple, and itself but not is or red. That is a future word. So this is basically what the masking does. And then calculate the attention matrix. It's basically softmax algorithm are based on the exponential z. Um, okay. Um, so red can see all four words. Okay. So and so what you can see here is that um, the letter words. So when this is here, then the next words are not seen. This um, this apple, and then you cannot see, and so forth, isn't it? So now we visualize the attention pattern. So how the weights as a heat map, so we can visually identify which word pairs have strongest connections in the attention matrix. The rows are word doing the looking, the query part, and the columns are the word being looked at, okay, the key. And the cell value is what fraction of attention of row word pairs to columns of word relate. Okay? So the dark blue cells are high attention, light red cells are, of course, less attention. Okay, so let's see. In a causal, so again here, so it's causal, so the letter words don't appear. So, I mean, of itself tends to be really high. So apple is, of course, related to apple very highly. But here in the red, look at it. Red is really highly related to apple, for example, isn't it? Right. And then calculating the attention head output, blending the information, it's this attention matrix times the value, which will get you the value it carries out, okay? And then we concatenate the output. Okay, so putting this all together, You can see here the setup. So the causal and non-causal experiments, like where you have the mask or not have the mask, you can see that the bird style, which goes back and forth, you can see also the future. So Apple actually is related to red. It's not supposed to see it, but yeah. Okay. And then the number of heads, like if you have a four-head relationship, then you can do this. Okay. But anyway, so this is sort of showing you how transformer attention algorithm works in terms of calculation, the arithmetics I just showed you, and what at the end of the day it tries to achieve, like giving you some insights. Okay. Thank you for watching this episode.